In this video, we're going to start with the basic skills that you're going to need for Chapter 10 as just a little refresher. So you should have a worksheet in front of you already. Before we do any of the questions, you should pause it and have a go for yourself. So for example, in this first question here, you're asked to resolve the following into IJ components. So for A, I'm going to do it now, but you should have a go at doing it yourself as well. If you know how to do it already, pause the video and have a go. Okay, so first thing that we have to do is I'm going to draw on this little diagram. So here I've got an angle of 20 degrees and this is a 6 Newton force. Now the x-axis is increasing because it's going that way, meaning that it's going to be positive, and the y-axis is increasing because it's going up to make this vector. If I draw the two component vectors, they look like that because it goes nose to tail, nose to tail. Okay, so all I have to do now is put it into the components. If I think about this as being a trigonometric ratio, this is the adjacent side and this is the opposite side. And this is the hypotenuse. Now we know the hypotenuse, so we're going to start transposing that formula. So if I'm looking for my x coordinate, which is the one that's going along here, that's going to be cos, because it's the adjacent and the hypotenuse. So cos theta equals the adjacent over the hypotenuse, which is going to be cos of 20 degrees is equal to A over 6. Now I can grab this 6 and move it up there to get A on its own, which means that now I'm going to have 6 cos of 20 degrees. Okay, make sure that your calculator is in degrees for this. So that's going to be positive 5.638I. So the length of this line here, or from here to here, on our plane is going to be 5.683I. Now, this over here, it happens all the time because we're looking for this value. So instead of doing all of this working out, I'm now just going to remember it as the formula of the hypotenuse is equal to cos theta I, and if it's going to be the sine component, now I'm not going to put the j and the I on the end here, because it's in relation to where we're looking on our triangle. You don't always get the angle parallel to the x-axis, so you just need to be wary of that. Okay, so now plus the next one I'm going to do is going to be 6 sine 20, and that's going to give me the opposite. So plus 2.05j. So this vector here can be expressed by this in component form. Now we're going to do B. So all I have to do, it's got a magnitude of 7. So 7, now if I think about this as a triangle, in there we've got a right angle, and over here we've got our angle, meaning that this is the adjacent side again, this is the opposite side. That's why it's going to be cos for the I component, because the I component is the adjacent, which goes with cos. Cos 35. Now this one, the x-axis is increasing, but the y-axis is now decreasing, it's going down. So minus 7 sine 35. Okay, and that's going to give you 7 cos 35, 5.734 minus 7 sine 35 minus 4.015 if I'm rounding to 3 decimal places, and that is your I direction and that is your J direction. Now we're going to do C. So I'm going to have 5 cos 15 degrees and 5 sine 15 degrees. Now our x component is going this way, meaning it's going to be a negative. And our y component is going down, meaning it's also a negative. So 5 sine 15 in the calculator gives me 1.294 if I'm going to 3 decimal places, and 5 cos 15 gives me minus 4.830 if I round it correctly to 3 decimal places. Now, there's no reason why I'm jumping between 2 and 3 decimal places. Normally, we would go to 2 decimal places as standard. So that's all you have to do for resolving. The only thing you really need to make sure of is that this angle is the angle that is parallel to the x-axis. Okay, so let's move down the page. How do I move this thing? Okay, there we go. Okay, so determine the resultant force. Again, pause the video, have a go at this yourself. So add all the I components together and then you add all the J components, and that's going to give you the resultant force for this. Now, the reason why that's happening is because the formula that I use is that 0 is equal to F1 plus F2 plus F3. So really this is finding this section in here. Okay, so if I add all of my I components together, 2 minus 2 plus 7 will give me 7I. And if I do minus 3 minus 1 minus 6, that's going to give me negative 10J. Okay, so the resultant force of these three is going to be that. Now we're going to do B, doing the same again. So these ones all go together. So 8 minus 3 makes 5, plus 5 makes 10I. And 2 minus 2 makes 0, plus 0 means there's no J component. This thing is horizontal, like that. Okay, so using what we just figured out, we're going to now calculate the magnitude and direction of our resultant vectors, which means we're chucking them into this formula and that formula. Now, when I'm talking about it being in this formula, we are expressing the angle as the one that is on the x-axis. So it's the angle from the x-axis, so that means that it can either be like this angle in here, or it could be this angle in here, or it could be this angle in here, or this angle in here. Okay, so let's start. So we're going to calculate the magnitude first, which means we're going to take the square root of each number squared. Which gives me, as an exact value, 149. Or if I want to put it as a decimal, it gives me 12.20. Now, 1 if I round it correctly. Now, if you're looking at the textbook, it tells you to leave it into exacts, but they also jump around a little bit with converting it to exact numbers and not. So do whatever makes you happiest at this point. Okay, so now let's find the angle. Tan theta equals y over x. So this is your y value and that's your x value. So negative 10 over 7. Now to get theta on its own, we take the inverse of tan, negative 10 over 7. So make sure your calculator is in degrees. That gives you negative 55 degrees, meaning that this thing is down here at negative 55 degrees, and it has a force of 12.21 newtons. So that's what we've really calculated by finding the magnitude and the direction of this diagram. Okay, now let's do the same for the second example. Now in the second one, we only have an I component. So when we work out the magnitude, square root of 10 squared plus 0 squared is going to give me 10. And when we work out the angle, tan theta equals 0 over 10. So theta equals tan of 0 degrees, inverse tan of 0 degrees, which just gives me 0, which means that it is on the axis. So if I'm drawing this thing on a plane, especially because it's on the horizontal, that's the vector. Here, I'll change colours. This thing here is the vector, and it's got a length of 10. Okay, not hard once you draw it. It's pretty easy to see what's going on. Okay, so we're now going to look at the diagrams and show the component forces. So this just means that, see how I've got this N force here? Now, that N force is acting on this plane. Currently, that N force is perpendicular, but it's being dragged down by this force. So it's got an equal and an opposite. So if I break this one down into what's actually happening, if that's the force of N, that's its opposite force. Now, that's the one that's stopping it from flying off into the distance. If this is my force going that way, then the force that's stopping it is going that way. Okay, but instead of drawing it next to it like that, we put it down here like that. So now, if I want to show the component forces and use a highlighter to show the components in the I direction. So in the I direction, if this thing is parallel, or we're using this slant as our new I-axis, then this one and this one are the ones that are going to be in the I direction. Now, really all that means is if I had setting out for this, it means 0, this force plus that force should equal 0 if it's in equilibrium. So F plus whatever that one is equals 0, okay? And then if we're looking in the Y direction, this one and this one are working in the J direction, sorry, not Y. Not hard once you draw it, but you've got to draw it first. Okay, so with B, first one we're going to do is that the N force has got one acting opposite. Then we're looking at this force here. Now, we can see that a strap is pulling it, and this time it's not parallel to the axis like this. This time it's pulling it in an upward direction, but that can really be expressed as an I and J component. So that's why this section here has something acting in this direction, and it's made up of a second vector that goes in the up direction as well to get us that F diagram. Now, one thing that we didn't note in the first one that we're going to note in the second one is the direction of the vector. So if I'm adding the vectors together to let it equal 0, this one is going to be the opposite sign to this one. So if that's moving in the positive direction, that's moving in the negative. So I would have to do 0 equals the blue minus the pink, because the pink is going in a negative direction. Okay, so anyway, now I'm going to highlight the forces. Sorry, we've missed one. Maybe we didn't. I'll double check before we have class. So anyway, this one, the one that's going in the J direction is this and this. The one going in this direction is this one, and I'm pretty sure that, I'll check again, but there should be one going in this direction too. Because this is being pulled that way, there should be an opposite reaction going in that direction. So we'll have two things to add together there. Now, that would make sense too, because this little guy is missing his friend, so he should be going that way like that. Okay, when we're looking at a force like this, and this is what I was talking about before. So maybe we've got a normal reaction and you've got something being pulled down, or it's sitting still, it's hanging by a string, and this is the weight that's pulling it down. Now, if I'm resolving these forces, 0 is going to be equal to N is acting in the positive direction because it's going up, and mg is in the other direction, acting in the opposite way. That's why it's going down. So it's negative. So the forces that are going in the same direction, though, these two. Okay, notice that each time that I'm talking about these things, you're only adding forces that are in the same direction. So I would do 0, this one plus that one, and I would do 0, this one plus that one. Okay, when I say this one plus that one, I mean account for direction. Okay, so this diagram here is very similar to that one, so you can have a go. This diagram here, when I look at anything that's not parallel with the axes, I know I can break it down into components. So there'll be one going that way, one going that way, one going that way, one going that way. Now I'm going to highlight all of the ones that are parallel on the y-axis. This one is parallel, this one is parallel. These ones are parallel. Next thing I'm going to do is I'm going to highlight all of the ones that are parallel in the j-axis. So this one, this one, this one, and this one. Okay, and then that's how I break down my diagrams. So then I only start looking at things that are in the same axis and resolving them to equal 0. If it's something that's moving, if it's got acceleration, that means force equals mass times acceleration. So instead of letting it equal 0, I let it equal ma. Now, I swear that there is more to this. Oh, yeah, we skipped question 4. Okay, so question 4 is Lamy's formula. He is a very convenient thing to have because it's using sine rule to solve for stuff. Now, a lot of your force diagrams can be solved with Lamy's theorem instead of breaking it down into component form and then using that to calculate the magnitude and direction. This will calculate the magnitude and direction for you straight away. The only thing to really note here is that when you're calculating the magnitude and direction, you want to relate it back to one of the other axes. Okay, so let's start with an example. So this is our formula here, where our first force is opposite to alpha, our second force is opposite beta, our third force is opposite, I don't know what that symbol means. We're going to call him delta today. All right, so notice that F1 is opposite and F3 opposite and F2 is opposite. So each time I'm looking for these patterns. So if that's F1, that's alpha. So I can start filling this in now that I've spotted the pattern. So F1 is going to, we're not sure yet, but we know that delta is 30 degrees. We know that F2 is something we're not sure of, and we don't have beta. But the thing that we do know is that all of these angles should add up to 360. So I can find beta by doing 360 minus 30 minus 120, and that's going to give me 210. Okay, and the last one, we have a full set of information. So the force is 10 and the angle is 120 degrees. So this is the full piece of information here. So I'm going to set that up first. 10 over sine 120. Now the things that you'll get incorrect here are you might not have your calculator in degrees, and it should be because this is in degrees. Okay, now we're going to solve for the second force. There's no reason why I'm going the second one first. It's just what I looked at first. So F2 is sine of 210 degrees. So I'm stealing that from there, and now I'm going to solve. So this is on the bottom, which means it's being divided, which means it's going to come up and multiply the numerator of this fraction. So F2 equals 10 sine 210 divided by sine of 120. Now, in an exam, these questions might come up in the tech-free section, and if they did come up in the tech-free section, it would do that by making these exact values. Now, I could do that for this and for this. This one doesn't really have an exact value, though. No, it does. It does definitely have an exact value. All right, so negative 5.77. newtons of force in the F2 direction. Now the F3 direction, let's see. No, F1 is what we're looking for. So F1 is equal to sine of 30 is equal to 10 over sine of 120. Grab this, put him up there. F1 equals, now sine of 30 is a half. So half of 10 is 5. Now sine of 120. 120 is over in this axis, and it makes an angle of 60 degrees with the x-axis. Sine is positive there, which means I can look for sine of 60 degrees. The sine of 60 degrees is root 3 on 2. So root 3 on 2. Now, anytime that I've got something divided by something else, I know that I can flip the fraction and change this to a times, which means that this is going to turn into 5 times 2 makes 10 over root 3. Then I'll rationalise my denominator by timesing the top and the bottom by root 3, which will give me 10 root 3 over 3. Okay, and that would be my answer in exact form if I needed to solve it that way, which would be a good question to have on a tech-free exam. Okay, next thing we're going to do, this one here. So, first I'm going to assign my variables. I don't know this one, but that is 45 degrees. F2, I'm going to call that the 6 newtons and the 135 degrees. F3 is going to be 8 newtons, and I'm going to solve for this one by doing 360 minus 135 minus 45. So now, all I have to do, F1's my only unknown, sine 45 is equal to, I'm going to choose the next one below it, no real reason, doesn't really matter, sine 135. Okay, I'm not going to bother doing this with exact values. You could try that as a little extension for yourselves. I'm just going to chuck it straight in the calculator like this and get my F2 force. Okay, and that gives me a good old answer of 6 newtons. So this one up here is 6 newtons. Now, when I calculate that force, if I work this one out, okay, and I work out that that 6 Newton force, this F1 force, and in here is 45 degrees, and I can say that F1 acts at 6 newtons of force against the other 6 Newton force in the clockwise direction at 45 degrees, or at an angle of 45 degrees. Now, these are the key skills that you need to be successful in the next unit that we're doing, so in Chapter 10 and 11. If you get these basic skills down, meaning that you can convert it to component form and you work out how to do the sums, then you'll be sweet. This will be an easy topic for you. But these skills are what you need to know first.